Aerobic adaptations. Endurance training requires the athlete to train nearer their VO2 max. For example, the high intensity interval training for a triathlete in order to improve their efficiency of providing the body with oxygen. The graph shows how during a steady state exercise, the athlete's breathing rate should plateau, suggesting that their body can access enough oxygen. Training at high intensity will mean that the athlete's body can work sustainably in lower intensity exercise. On the other hand, less intense training for a marathon will allow their body to familiarise itself with the intensity and demands, showing that it will be competent in the race. The athlete's heart during high intensity interval training will have to supply the body with a high amount of oxygenated blood, then return nearer resting levels before it starts again. This means that the heart will experience cardiac hypertrophy of the myocardium because the stronger it gets, the less it needs to work. This means that it will comfortably supply oxygen for the athlete during a lower intensity race because it has the ability to do so for maximal training. From this, the resting stroke volume of the athlete will rise because the heart is pumping more oxygenated blood than before. Consequently, the resting heart rate will fall because there is more than enough oxygen with each beat. Figure 1 shows how heart rate increases through the multi-stage fitness test. A fall in rested heart rate will mean that the athlete's heart rate at each stage will be lower, which will increase the intensity that they can work at. Furthermore, the cardiac output will increase slightly because more blood is being pumped, but there are less beats per minute. As a result, the triathlete will have a greater heart rate range, therefore can work for a higher intensity during a race due to the rise in volume of oxygenated blood leaving the left ventricle. As oxygen is present during aerobic exercise, the alveoli and their capillaries are constantly being used to diffuse oxygen in for produced carbon dioxide in external respiration. This will mean that from training, the surface area of the alveoli, as they are needed to undergo gas exchange more, this will mean that there is a greater potential volume of gases to be diffused. The abundance of oxygen detected during this training will trigger the production of more red blood cells in the blood. This will mean that there is more hemoglobin. This is called hematocrit. This will mean that there is more hemoglobin that can transport oxygen from the lungs to the muscles to use for energy. This will increase the amount of potential energy that can be generated, supplying the muscles for longer. Training will increase the volume of plasma in the blood. This will mean that the blood has a lower viscosity, which will produce better blood flow. This will mean that blood pressure is lower, preventing possible conditions like stroke and heart attack. During endurance training, the athlete will have to work at 100% effort. This means that they will need to participate in forced expiration as well as inspiration. From this, the respiratory muscles will be required to stretch further than normal. As a result, they will become stronger and allow more stretch. Furthermore, they will be able to bring in and let out more air, which is a higher tidal volume. Higher resting tidal volume will allow rest and breathing rate to decrease as more air is entering the lungs and therefore not as many breaths are needed. From these outcomes, the minute ventilation will be positively impacted slightly, but not a lot. The graphs show the breathing rate and estimated minute volume during the steady state exercise test. For each intensity, they are both seen to plateau. They show that the intensity and the oxygen demanded have a linear relationship. Therefore, the high intensity interval training will make the body more efficient when it comes to consuming air, which will lower the heart rate so that they can work harder with the same oxygen consumption as before. Training maximally will mean that the oxygen deficit is greater than during the event. From this and the extra oxygen in the blood from the additional red blood cells, the athlete can make the deficit lower, and therefore the epoch stage of the recovery will be shorter. Aerobic events like the marathon recruit the slow oxidative and fog muscle fibers. During the lower intensity continuous training, the athlete will recruit these fibers to produce slow contractions for a longer period of time. From this, the muscles will experience hypertrophy because the fibers are gaining more myofibrils, therefore increasing the muscle in diameter. From this, The greater presence of the slow oxidative and fog fibres will mean that the athlete can generate these contractions for a longer time. With training, the muscle's oxidative capacity will rise because of an increase in the number of mitochondria in the muscle cells, which are responsible for creating energy for the cell. This will mean that there is a greater quantity of enzymes, therefore energy can be produced quicker, providing more contractions. The muscles also get increased ability to store oxygen in the form of myoglobin. This means that there is a more local store of oxygen to be used for energy, positively impacting the runner's performance. The increase in number and size of mitochondria is called cellular adaptation from training, also increases the level of aerobic enzymes. This will improve the ability of slow twitch muscle fibers to resynthesize ATP, allowing the athlete to perform for long periods of aerobic exercise. Respiratory exchange ratio illustrates the percentage of fats and carbohydrates that are being used for energy production. It is calculated by dividing the volume of carbon dioxide produced by the volume of oxygen consumed. For a triathlete, the RER should be above 0.84, proving mainly fats used for energy. This can be used in conjunction with glycogen sparing, which is the process of saving stored glycogen and using more fats for energy. A week before the race, the athlete should cut their carb intake and use up nearly all of their glycogen stores, called carbo-depleting. This will mean that the body preserves it. 3 days before the race, the athlete should intake high amounts of carbohydrate, therefore the body will store it as it does not want it to run low. This is called carbo loading. From it, the athlete does not want to build up lactic acid because it will cause fatigue in the muscles. From training, as shown by the graph, the athlete's OBLA will be delayed. This is called buffering. This means that the athlete can work at higher intensity before they build up lactic acid, which will be when they have to stop.